Every bit of science that you will find will have, it will go down to the molecular level, and even electricity. What you're really seeing when you get that shock, when you hit that doorknob after you've been statically electrically charged by rubbing your feet on the floor, what you're really feeling is a little bit of electricity there, where the atoms in your hand and in the doorknob are actually reacting to each other. And we call that static electricity. Even though static electricity is just kind of something that they're having, it doesn't really hurt us at all, but sometimes it can. Sometimes it does get to be on the dangerous side, and that's when it's certain elements that are being electrically charged. And it's not the electrons that are leaving the atom then, it's actually the nucleus. The nuclear weapons were one of the most significant times in history, and it was all actually because of electricity. It's just that splitting that atom apart, and that is, radioactivity is just kind of a form of electricity. One thing that you get when you use electrical safety is that you must, if you have directions, follow them to 100% accuracy. And what I mean by saying that is the exact measurements, the exact amount of something, the exact element, the exact amount of everything, because sometimes one little thing can really send the entire thing into a deep dark hole. That's why it is very important to know these electrical safety rules. It's also important to be careful of your surroundings. First, before you turn that power on, look around you. Is there, and I'm trying to stress this with water. Electrocuted water is like the bull in the china shop. It is just waiting to create trouble. If you were to step in electrocuted water, it would send an electric pulse all through your body. Now that itself is really fine. It won't really kill you, but the after effects will. See, that stuff interferes with the beating of your heart, and sometimes it changes the pulse of the beating of your heart, and that's where things start to go downhill. Water is an essential element to life, but electrocuted water is just bad news. Don't electrocute it. It is highly recommended that when you work with electricity like this, you should probably wear safety goggles. It just, because that wire can spark at any time, and you don't want any of those sparks to hit your eye. And so you should always wear safety goggles when working with electric circuits and trying to get them right, and working with electricity like this, just in case that does spark up. Clothes, it depends on what you're wearing. Definitely lab vests if you're working something like this, because if it's especially woolen, that spark will probably create fire and will probably set you on fire, which probably won't make your day. And then finally, the fourth thing is you should probably always check your surroundings. Like if you have, again, make sure there's no water on you, because that can mess you up. Also, if you were to have all of the circuits in your house turned on, so if you say, oh, I just want to change this one thing, first turn your electricity off, because if you were to take that thing apart, it'll shoot out at you, and there's a spark there, and then you'll get sparked in your hand, and then it's just not fun. So always make sure everything is safe. Safety first before you do something with your loads. Um, and also plan ahead. If you were to say, all right, I just want to really change one thing. Well, maybe you should think of, yeah, I could do that and that could probably help, but maybe what elements would that create that may mess up everything else? Because remember, if you put that one in, it may blow your whole circuit and you need to start all over again by completely new materials. And, think about maybe what are the side effects of some of that. Maybe something will happen that I don't really want to happen. So that you should probably plan ahead when you do this. Using proper tools is incredibly important, and even it's the fifth rule here, it just really needs to be on the list, because I don't know, you touch that copper wire with just your bare hands, especially if the electricity's on. Yeah, there may be still some electricity in there and you may get shocked. So always be careful with what tools you're using. And just those skinny little dental gloves that you put on, they aren't going to do too much. Use an insulator. Now, an insulator is basically something that it doesn't allow electricity to pass through it, but it's kind of just something thick that electricity can't pass through. Such things are like glass, some kinds of wool, just something that's thick, insulation, and the walls of your house that's just an insulator. Something like that. Make sure you're using the right tools to put on your hands before you stick your hands in there. If you're using pliers, make sure you have the right one that won't cut the wire, and make sure to turn it in the right direction with the proper tools. Series circuits are circuits that, they're incredibly simple. Usually they have a power source, and then they usually have some kind of, so they have a power source, then they have a wire, obviously a path for the electrons and protons to move through. Then it goes up here. Usually one load, just kind of, you can have more than one load, but usually it's just one load like a light bulb. A light bulb is a series circuit. And then, of course, you need something to turn on. Unless you want it to be constantly on, you're probably going to want something to say, all right, yeah, I need to change something in here, but I don't really want to, remove the battery, because that could take a while. You need to get it back in there, and, that could take time. So, add in a switch, a button, anything that activates it. The battery you can't turn on and off. The battery is just, it always emits power. Now, a lever or a switch works when you when you break the circuit. We call it an open circuit. Now, an open circuit is when the positive charges, plus and minus charges, can't get through. Everything just stops and nothing happens. The circuit is open, and it's a stopped circuit. Then, when you complete the circuit back again, which is when you turn it on, the electrons can flow again, and you call that closed circuit, which means that it's just another way to say on. Parallel circuits are, I don't really want to say the opposite, but basically, there's more than one path. There's more than one wire. It's when you have the battery here, a wire going up here, a load here like a light bulb or something, and then over here you have like a music playing. So and then the switch right here. So you turn the switch on, it goes up here, it turns on the light bulb, but it plays music as well. And then they obviously both have to go till here, join, and then come back down to the battery. So basically it's kind of like that. There's two different loads, but they use two different wires. Now, if it was this battery power source, path, switch, wire, light bulb, go here, music, then goes back to the battery. It would be a series circuit. But the fact that it goes like this, or like this, and then they come back together, it's a parallel circuit. Which means, and usually what happens is, okay, battery here, here, light bulb, here, light bulb, here, light bulb. So usually it's kind of like that, which means 3 lines like this, parallel. So that's how you can remember the difference between a series and parallel circuit. And they are like 2 different things. And so basically a series circuit is a simple series, and parallel have usually parallel running wires. In circuits, there has to be a way for the wire to move through. And this is a lot to do with switches. So here's the power source. Wire here, switch here. And then pretend there's a light bulb here, and then it goes back down to the battery. So basically, you go to the light switch, you turn it on, open, closed circuit. Go here, it turns on the light bulb. Simple series circuit. But it's kind of important to understand switches, and this is another way to understand switches. It is electric currents. Now, electric currents have to do with a battery as well. Have you ever looked at a battery and said, oh, there's a plus sign on this end and there's a minus sign on the other? What it really says is plus is positive and minus is negative. So everything comes out of one end of the battery. It goes up to the switch, closed circuit, go through, turns on the light bulb, down here, and back to the battery. That is basically an example of an electric current. And again, open and closed circuits. You turn the circuit on, you turn the circuit, open circuit, closed circuit. Remember, this is a one-way thing. It's a constant, square, but it goes around and around, and you can't have it come out of the wrong thing. And if you have the things on the wrong thing, it'll actually, if it's sending out when it's supposed to send out, and you put it right here, then it's just actually not going to do anything, because nothing's happening. The battery doesn't really get what it's supposed to do, and then it juices itself up, and then it just doesn't work anymore. And then it actually just really kills the power source of the batteries. So basically, that is an electric current. Benjamin Franklin was a scientist that discovered electricity. At his time, many people were losing their houses due to lightning strikes. He decided that lightning may be just another form of static electricity. And so, he put a key in a jar, and he tied the jar to the string of a kite. He flew the kite during the storm, and then a lightning bolt hit the key, and it charged it. It sprays down, and that's a lightning bolt. Magnetars are just absolutely, I don't really want to say scary, but they are scary, but they're just really weird. We really don't know anything about them. Think about this. A magnetar is one of the top of the most likely of the very long list of how we think the Earth could end. And that sounds a bit scary, but we really don't have anything to worry about because the closest magnetar is so far away. The electromagnetic span of a magnetar is utterly humongous. On 2004, all of a sudden, an entire humongous shake rattled through the ground. And then there was an explosion in the sky. Everyone thought it was a supernova, but no. The closest magnetar, which is all the way across the Milky Way, crusts had slipped only a centimeter. But it had emitted so much energy, we felt it here on Earth, many light years away. That was the very first discovery of a magnetar. Thank you for watching.